questions that I'm seeing that. I remind you, discussion boards. I know I'm behind on getting some responses back to people who have participated in discussion boards, but I tried to spend some time last night doing a little bit of that, and I will get to you, I promise. I've loved reading some responses so far on the discussion board, so please make sure you look at those and participate in those as you have time. Any other questions from you guys? I don't see any in the chat. Okay. Well, we are going to get started. We'll finish up chapter 2 today, and then you should have all the info you need to complete the chapter 2 homework. And I encourage you spend some time on that today and tomorrow before you head into the weekend, because it is due, reminder, Monday night. That's chapter 2 homework on mastering. So let's get started. Let me share my screen. All right. And then also we have that quiz due by midnight tonight, quiz number 2. And I've had lots of questions on how do I see the right answers? How do I see the ones I missed? Reminder that the correct answers will be posted once everybody has completed the quiz. So they're not going to be visible, I think, until midnight tonight. But so you should be able to get on tomorrow. If you go into the grade book on Blackboard, go into the grade book and click on your grade. That should be clickable, or there's a little arrow beside it if you hover over it. And click into your quiz assignment. You should see the answers you put forward, and if they were right, and if they were wrong, and if they were wrong, you should see the correct answer. Okay, I definitely want y'all to be able to use those as a study guide for the exam. If you have any issues finding that or doing that, let me know, but that is how you do it. Okay. All right, so let's chat. As a reminder, where did we leave off Tuesday? So this was kind of our summary slide. Tuesday, we covered Dalton's atomic theory, the 4 parts of it. I want you to know all 4 parts and what they mean. And then we covered atomic structure, electrons, protons, neutrons, how they are arranged in an atom, their charges, their mass in AMUs, what their role is in the atom. Did anybody go watch the video from the TV show and how they explain the atom with the street gangs? If you didn't, you're really missing out. You should go do that. It's only a few minutes. And then we also talked about isotopes, okay? What A and Z mean, the atomic number versus the mass number. We talked about how different isotopes have a different natural abundance. They're present in different amounts in our planet. And then we also talked about how to calculate average atomic mass. This was the only math problem style that we worked from Tuesday. And I want you to know how to work a problem like that. In fact, here was the slide we did that on. Calculating atomic weight. We said it is a weighted average, all right? And here was where we calculated the problem. Okay, you take the mass in AMUs and you multiply it by the percent abundance as a decimal, and you do that for every isotope. Here we only had 2 isotopes. We had copper 63, and then we had copper 65. So we had 2 isotopes. If there was more than 2 isotopes, you would continue to add it up, do that multiplication, and add those all up for every kind of isotope. Okay. To get the atomic weight. So know how to work a problem like that is what I'm trying to say. So that's what we did Tuesday. Today we're going to look at the periodic table, how it's organized, what it communicates to us, what we can learn from that, and then we're going to talk about valence electrons, and that is chapter 2. And I love this slide. It always makes me think of my grandma, and here's why. So this slide says, here's how they really made the periodic table. It was one giant game of Tetris. Anybody play Tetris before? It's a great game. If you've never played it, it's a lot of fun. It's also very stressful when the pieces start falling really fast. But my grandma she is like a beast at Tetris, guys. There's one year for Christmas, we got her a Game Boy. Anybody play Game Boy still? Those a thing of the past? I don't know. I wish we were in person because people would nod their heads, and I can only see a few of you. Well, we got her a yellow Game Boy, and then my grandma's like 84 now, and she probably still plays it. But every time I'd go to my grandparents' house, I would try to sit down and beat her numbers in Tetris, and I never could. So anyways, That's my story about the periodic table in Tetris. But it's not how they created the periodic table. The periodic table is much more thought out than a game of Tetris, okay? So let's look at how it was thought out. First, we're going to look at how it was organized. So here's the two main ways it's organized. There's 118 elements here, give or take, and there is so much information packed in this table that I bet you never knew. So the main ways it's organized are horizontal and vertical sections. Okay, that's the first thing. So a purple section, this horizontal portion, is called a row. Sometimes it is also called a period, but I commonly find myself using the word row. So I want you to know when I say row, I mean a horizontal section. The red portion is called a group. That's what I call it. It's also known as a family or a column. But I find myself using the word group most. So if I say row 2 or group 1, I want you to know what I mean when I say group 1 or group 5 or row 2 or row 5, okay? I'm talking about a vertical or a horizontal portion of this table. All right, so here's that information here. Now you see the same periodic table, and you see 4 different groups that are highlighted. All right, these 4 groups right here, 1, 2, and then these 2 over here, these have common family names. So there may be times I say group 1 or group 7, but there also may be times I use their common family names, and you need to know the common family names, not for all the groups, but for these 4, you'll need to know these. And so we'll go over what those 4 are. Another way to arrange the periodic table is the sections you see here in red, blue, and green. All right, so what is the red section? These are what we call, this is the sum total of all the main groups. These are main groups. I want you to know how to count main groups, and we'll do that in a little bit. And then the blue, these are transition metals. Okay. These are also groups, okay? Each of these sections are groups, but they're groups of transition metals. And so we don't count them among the main groups, okay? That's why they're not red. So we count those differently, transition metal groups, we count those differently than we count main groups. The main groups are just this portion over here and then these 2. These are main groups. So the green part, these are the lanthanides. And the actinides. Now, where did we get those names from? If you notice this little arrow right here pointing to the green section, it is coming from right in between these elements. So all of these green elements actually are wedged up in between these 2, these 4 elements, I should say. So these bottom 2 rows of the periodic table, these rows, they're actually a lot longer, but for space sake, to keep things more concise, they pulled them down beneath. So they're not, this green portion is not its own separate thing. It's part of the periodic table, but they fit right here. And you'll notice if you look at the atomic number, it jumps from 57 to 72. That's because you should actually continue counting down here with 58, 59, blah, blah, blah. And then notice the names of these. This is lanthanum and actinum. So that's why they decided to call this row is the lanthanides, and then the bottom row is the actinides. So we didn't just come up with a difficult name for fun. They just named them after the elements through which they follow, okay? Now, we're not going to study the lanthanides and actinides in this class. We're going to spend the most of our time on the main groups and the transition metals, so the red and the blue portion of this table, all right? Another way to organize this thing is right here. You've actually seen this picture. The very first lecture we did, we had a picture of the periodic table color-coded like this. We have a yellow, purple, and a blue section. Everything in yellow is a metal. All of these, so you see the periodic table is mostly metals. And what state of matter is a metal at room temperature? At room temperature, metals are solids. right? Now, can anybody think of one exception? There's one metal that is a liquid at room temperature. Anybody know what it is? I bet you can think of it.
It's mercury, right?
Yeah, mercury, right here. That's our exception. Mercury is a liquid at room temperature. And that is some bad stuff. You don't want to play around with mercury. Okay, the purple, which is like this diagonal stair-stepped section over here, these are called metalloids. Why are they called metalloids? They exhibit properties of both metals and nonmetals. Kind of, some of them can conduct electricity, not very well, but they can. Some of them are gases naturally, like the nonmetals. So that's why we just call them metalloids. Okay. Now the blue elements, these are non-metals. So most of these are going to be gases at room temperature, with the exception of our friend bromine. This element is a liquid at room temperature. Okay, so we have two exceptions, bromine and mercury. Everything else is either a solid or a liquid, depending on if it's a metal or a non-metal. So if I said, what state of matter is zinc, or what state of matter is magnesium at room temperature, you should be able to tell me, a solid. Or if I said, what state of matter is fluorine or nitrogen, you should be able to tell me it's a gas, okay? Based on how this table organizes it and color codes it. So there's that. Questions so far? Now you'll also notice that this ropes off, or labels at least, the transition metal groups versus the main groups, and there's more main groups over here. And if you're looking, look at the way this is kind of numbered, and then they also use letters. So main groups have an A, the letter A attached to their numbering. Transition metal groups have a B. So if we're counting main groups, we skip the transition metals. Anything with an A, we classify as a main group. So it'd go 1, 2, skip a few over here. Here's main group 3. Here's main group 4, 5, 6, 7, and main group 8. Okay. Okay, so, sorry, let me respond to a private comment real quick. So I want you to know how to count main groups. I want you to know how to count transition groups, all right? Total, there are 18 groups, columns, but there's only 8 main groups, so know how to count those. All right, now I did tell you that 4 of those main groups have common family names, so we're gonna see what those are now. We're gonna start with main group 1 and its common family name. Notice over here is main group 1, boxed in red, but we're not including hydrogen, okay? Hydrogen is not a metal, it's a non-metal, and so it's kind of, we don't put it in this group, even though it is technically placed there. It's not a part of the alkali metals, because we know hydrogen is a gas, it's not a metal. So common family name here is the alkali metals. Now here's what you need to know about them. It's stated down here, but they are very, very reactive. In fact, we're going to watch a video or two in just a second of how these elements react with water. So they're all metals. They react really well with water, and lots of other things too. And because they're so reactive, we don't find them as pure substances like out in nature. We're not just going to walk across a pure substance of potassium or a pure portion of sodium. They're going to be combined in a compound, all right, which is what that says. They're never found in nature as pure. They're always in a compound form. All right, I'm going to show you 2 quick videos. So I'm going to stop sharing my screen for just a second. I'm actually going to share my desktop with you. And I'm going to slide over here. So can y'all see this YouTube video? All right, first off, before I play it, this is a piece of sodium. It's a small piece. You can see how big it is in relation to some fingers here. And what do you notice? Whoever is doing this, they're actually cutting into this metal with a knife. So point number 1 is these metals are actually pretty malleable. You can cut them with a knife. They're not like steel or iron or things that you would never be able to cut with a knife. Okay, they're pretty soft metals. And then what do you notice when he has cut? What do you notice about that freshly cut surface? What is it? How does it look? If you had to describe that with one word.
Smooth.
Smooth, shiny, okay, lustrous. These are shiny, lustrous metals. Sodium, potassium, the alkali metals. Now we're going to look at how it reacts with water. I'm not going to turn the sound on. So they cut it. I think he takes like an electrode. I'm not sure what they do with it. I'm going to skip ahead to when they drop it. Okay, drop it in water. And you notice some reaction. You see some, it kind of looks like smoking. I think they zoom in on it. Yep. So there's that little bead of sodium. It's definitely reacting so much to the fact that it's moving around quite a bit. But nothing crazy explosive. I used to show a different video of sodium reacting with water, and a big enough piece would create some fire and some explosion, and that was more fun to watch. But that I could not get that link to work today. So there it is. That's the reaction of sodium with water. Now I want you to watch a reaction of, oh man, I gave it away. Potassium with water. Okay, this one's much more quick. I got the volume on. I want you to hear it.
Yeah. Ready? Yeah.
Let's watch it one more time.
Yeah.
Notice the size of the potassium and sodium, roughly the same here. But you get two completely different reactions. Okay. I am not that daredevil, so I'm sorry I'm not as cool of a science instructor as this guy. But let me go back to my Let me go back to the iPad here. Hopefully you can, that's selecting. There we go. All right, you can see my screen now. So let's talk about the differences. How were these two reactions different? We had, here is sodium. Okay, that was the first video. And here is potassium, both alkali metals. That was the second video. They're both group 1. They're both alkali metals. They're very close to each other on the periodic table, only one row apart. How were these reactions different?
One was more explosive than the other.
Okay, do you know which one? The second one? Do you remember which element that was?
No.
The second one was potassium, okay? So you're saying this one, potassium, was more explosive. I agree with you. I think it was quicker. Okay, it reacted more quickly. You saw the explosion pretty immediately as soon as it touched the water. Compared to the sodium. Okay, the sodium was actually kind of boring now that we watched the potassium. Okay, what do you think would happen if I took a hunk of, this is cesium, and I dropped that into water? Do you think I'd be able to get away quick enough, or do you think I would lose a finger or two?
I think it'd
Probably.
be a lot faster than the potassium.
Mm-hmm. Yes, it would. And so the trend here is that as you go down, they become more and more and more reactive, okay? So I bet francium is even more reactive than cesium, okay? So there's a trend here that I wanted you to see. All right, I put these links in. I tried to make this one work and it just wouldn't. So I found another link. I can share that link if anybody wants it. Just shoot me an email. So you didn't actually see this link, but this one is the one for the potassium and water if you want to rewatch that. Okay. Group number 2, common family name. These are the alkali. So very similar name, but alkali earth metals. And similar to your alkali metals, they're also very reactive. They're not as reactive, so we're going to say they're less reactive. But they still are reactive, just not as reactive as group 1. All right, so similar to group 1, we'll find these in compound form. You don't really see them as pure elements a whole lot. And these are things like calcium, magnesium, barium, okay? That's alkali earth metals. All right, let's keep going. Skip over to main group 7. So remember the A denotes that it's a main group. So we're talking about main group 7. They are called the halogens. And hopefully, maybe some of you have heard these names before. If you haven't, it's okay. So that's fluorine, chlorine, bromine, iodine. These are your halogens. And what do we know about them? They're colorful. They're also corrosive. So they exist as gases, everybody but bromine, at room temperature. So they're nonmetals. And they, what does this say? They commonly react with group 1. And they form salts. Can anybody name a very common type of salt between a group 1 and a group 7?
HNCl.
NaCl. Yep, sodium chloride. Now, the crazy thing in here, I put this link if you want to go watch a quick how these two react together. So chlorine is a colorful kind of corrosive gas. We already saw that sodium metal is this very shiny, lustrous metal. So you put those two things together in a beaker, and here's what happens. You get flames and fire, and you get a violent reaction. But what does it produce? This very docile, edible salt. Okay, so chemistry is one of the cool things about chemistry is you can take two things you would never eat, two harmful things. They have this violent reaction, and you get something totally edible and useful that we use every day. So, but we call the product between a group 1 and a group 7 a salt. So potassium fluoride would be a salt. Sodium chloride is a salt. Lithium bromide, okay? Anything that has a group 1 and a group 7 is a salt. All right, the last common family name that I mentioned is the noble gases. That is main group 8. Noble gases. Okay? Helium, neon, argon, krypton, xenon down here. Sounds like a character from like an Avengers movie. Xenon. That's the noble gases. Now, the noble gases, anybody know anything about the noble gases? Are they reactive? Do you think they're not reactive? Anybody know? Very stable. I like that choice of word, Courtney. They're very stable. We're going to talk about why they're stable today before class is over. But because they're stable, they're not reactive, okay? So we say they're inert. They're not reactive. Okay, they're just fine by themselves. It's funny, my daughter, she just turned 2. She just had this cough for a little bit, so we couldn't take her to daycare for a little while because like COVID, daycares are so tight. Like you have to have a doctor's note for them to be cleared to even come. So we go to the doctor's office to get a doctor's note this week, and the doctor came in and was like, "How are you doing?" And she goes, "I'm just fine." She's 2, guys, and she's like, "I'm just fine." So anyways, the noble gases are just fine. They don't need friends. They're your introverts. They don't want to react with anybody. They're fine the way they are because of what Courtney said. They're very stable. And we're going to talk about, again, why they're stable in a little bit. So we'll come back to that. But you do not find them in compound form. You find them as a pure substance. All right, pure substance. All right, so those are the common family names, your alkali metals, alkali earth, halogens, and your noble gases. So know those. Know how to count main groups. Know what the word row and group means. And now we're going to talk about a characteristic of the periodic table called periodicity. What that is, it's a systematic trend in certain properties. Because of the way things are organized, if you plot out certain properties on a graph, you'll see trends. So let's look at this. It's actually really cool. We had lab this morning. We did our wet lab. Some people did. And there was at one point I heard somebody say, "Man, this is cool." And I said, remind yourself of that in 6 weeks from now, that chemistry is cool. You said it yourself. Guys, don't forget how cool it is, okay? Periodicity. So let's look at this. What do you notice about this graph, first off, before you even read the X or Y axis? What do you notice?
Radius gets higher.
You're reading it. You're observing even more than I want you to. There's spikes, right? There's periodic spikes. A pattern. Thank you, Brennan. You see these periodic spikes. All right. Now, what are we graphing here? We are graphing the elements by increasing atomic number, which is just the number of protons in the nucleus, right? And we're graphing that against the atomic radius. Now, let's all remember what a radius is. If we have the nucleus of an atom here, and we have the electron cloud here, the radius is the measured distance from the edge of the electron cloud to the nucleus. Okay, so I'm going to abbreviate R. That's the radius. So if the radius is increasing or decreasing, the size of the atom is increasing or decreasing, right? So it's just a means to measure the size of the atom. Now look at the unit here. PM. Anybody? That doesn't mean time, all right? What is PM? You don't have to know this. It's a prefix. Anybody know? It stands for picometer. Okay, so it's a very, very, very small distance. Okay, so looking at this now, we have these trends. Let's look at the top of each spike or peak. What elements are these? Li, Na, K, Rb, Cs, Fr. Let's look at a periodic table. What do you notice about those elements?
They're in the same group.
They're in the same group. They're all group 1. All those elements that were at the top of each peak are all group 1. Okay, now let's look at the ones labeled at the bottom in blue. Hydrogen is an exception here. It's the smallest anyways, but let's look at the others. F, Cl, Br, I. What do you notice about those?
They're halogens.
They're all halogens. So we see that the halogens are the smallest atoms on the periodic table, and we see that the group 1s are the biggest atoms on the periodic table. Now, if I zoom in, let's just pick a random trend here. Let's start with K, and let's go to Br, which, by the way, let's look at this. K is here. Well, it's probably too thick. K is right here. And Br is right here. The point I'm trying to make is they are in the same row. So we are about to assess how the size of an atom changes as you go across the periodic table from left to right. So let's look at this. K is the largest, and then it goes down, 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 and bromine is the smallest. So as you go across the periodic table from left to right, atomic radius decreases. We're going to write this out in a trend in just a minute, but make a note of that. And then it's the same. If you go down to the next row, because rubidium is right beneath potassium, as you go across, the size of the atom gets a little bit smaller until you hit iodine, okay? And look, iodine is the smallest one there. And then it shoots back up to the point of a peak, okay? So the group 1s are the largest. And then also another trend I want to point out, if we are looking just at the group 1 elements, lithium is the first group 1 element. It's on row 2. Sodium, so it's on row 2. Sodium is on row 3, so it's one row beneath. Potassium is row 4, it's a row beneath. 5 and 6. So as you go down in rows, okay, as you go down group 1, what happens to the size of the atom? The atomic radius increases. So let's write this out. Let's write this out. Oh, look, I put a slide in just so we could do this. I'm gonna draw a periodic table. I'm really good at drawing these. Close enough. Okay. As you go from left to right, what we found, what was the trend? Atomic radius does what? It decreases. And then as you go from top to bottom, we said atomic radius increases. I want you to know these trends. If I gave you 4 random elements, If I said, sodium, and if I said chromium, sulfur, and chlorine. 4 random elements. I said put these in order of increasing or decreasing atomic radius. If you know these trends, you can do that. Okay? In fact, why don't we do that? Sodium. I'm going to erase a little bit. So sodium is right here. And then we had chromium is right here. And then we have, what else did I say? Sulfur was right here. And chlorine, right next door. If you had to put these in order, as you go from left to right, you should be able to do that. So which one would be the largest? I'm hearing someone try to say it.
Sodium.
Huh?
Sodium?
Yeah, sodium would be the largest. And then, well, what do you know? I already ordered them for us. They're already in order, everyone. You're welcome. Chromium would be the next because it's the next most, or the next element furthest to the right. Sulfur is the next furthest to the right. Chlorine is the most furthest to the right. Well, anyways. Okay, so I want you to know that trend. I want you to be able to order atoms in order of increasing or decreasing atomic radius. Okay, next we're going to talk about valence electrons, and we're going to spend the rest of our time on valence electrons. All right, here we go. So we have 3 pictures of an atom here, and you are most familiar with the middle one, okay? Here we said this was the nucleus. We said this is the electron cloud. And we said there's electrons zooming about in the electron cloud. That's what we said on Tuesday, okay? Don't worry about this picture over here. If we were getting into electron configurations, we would get into that, but you know, we used to do that in this class, so count yourself among the lucky because we don't memorize those anymore. But today we're going to learn why this picture on the left also is a very, even more so accurate picture of an atom. So I call this the kind of the layered onion look. We see different circles, concentric circles around the nucleus. And each one gets a little bigger, like layers of an onion, okay? So what you're going to find out is electrons can be on these different layers, all right? Different distances from the nucleus. So as scientists looked at the periodic table and learned more and more and more and put it in just the perfect order, they found those periodic trends that we just talked about. And then they began to ask, well, why are these here? Why do certain elements behave the same way based on certain properties? And it all has to do with the arrangement of an atom's electrons. They figured out that how those are arranged, if there's similarities in how electrons are arranged, it determines an atom's or an element's chemical properties. And that's actually what we said on Tuesday when we said, what's the role of an electron? We said it determines the chemistry. It's responsible for the chemistry or the reactivity of an element or an atom. If we have a test over this material, yes, I will supply you with a periodic table. And in fact, you might need a periodic table for the quiz. If you haven't taken the quiz yet, you can use your textbook, and there's a periodic table in the cover of your textbook, whether you have the electronic one or the hard copy. And you're okay to use your textbook, so you're okay to use that and the notes. You can use, so you can look at a periodic table if you need to. So yes, I typically upload what I call a resource page. So it might, for like exam 1, you'll be given the equations for like temperature conversions, remember Fahrenheit to Celsius, and you'll be given a periodic table, blah, blah, blah. So yes, you will have a periodic table. You do not need to memorize the periodic table. Okay, so the arrangement of an atom's electrons determine its chemistry. And then that arrangement, well, what's determining how electrons are arranged? Is it random? Is it organized? It's very organized. It's very ordered. That arrangement is determined by the location of the electron within the atom and the energy of an electron. So what we just said here implicitly is that different electrons have different amounts of energy based on their location. All right. So an electron on an innermost circle, I'm actually going to call these circles a shell. So any one of these circles, we're going to call these a shell. Okay. We could call them an energy shell. You don't have to know too much about the energy, but an electron on the innermost shell, so like this one is going to have the lowest amount of energy. And an electron on the outermost shell has the highest energy. Okay, so you can see based on its location in the atom, it's going to have a different amount of energy. And these things, believe it or not, affect how reactive an element is. So they can be on these energy shells. Where they cannot be between the shells. It could not be here. An electron could not be here. An electron could not be here. What's really funny, I told the last lecture class when I had a baby shower for when we had our daughter, our first kiddo, and someone got me a book that was Quantum Physics for Babies, and everybody laughed when I opened it. So like, haha, you love science, blah blah blah. And every time I teach this, I almost bring that book every time because it literally explains this in such simple terms. It's hilarious to me, but you guys actually might find it useful. This exact concept. And so, yes, I have read that to my daughter, in case you're wondering. She knows all about quantum physics. But what we call the amount of energy an electron has, there's a special word we use for it. I'm going to come down here because I'm going to draw a picture. We say electrons have, I'm going to use a fancy word here, quantize energy. I just want you to remember that electrons can't be anywhere. I want you to remember that they can only be on the energy shells, certain distances from the nucleus. And a good example for this, it's like understanding the difference between a ramp and a set of stairs. So if you are handicapped and you're in a wheelchair, you have to have a certain kind of access to any building you go in, right? And most often that's in the form of a ramp. So here's my drawing of a ramp. Okay. Now a ramp we know is different than a staircase. Here's a staircase, all right? On a ramp, if I'm walking up the ramp or rolling up the ramp, I can be anywhere. I could be here, I could be here, I could be up top, and I can be anywhere in between, right? All spots on the ramp are accessible, okay? A staircase is different. A staircase, you have quantized positions or heights you can be on the staircase. If this is ground level, I could be at ground level, or I could be on staircase 1, but I cannot be at any place in between, all right? I cannot be at this height or this height. I can be at ground level, or I could be at the height of staircase number 1. I could be at the height of staircase number 2, but I could not be anywhere in between on those heights, okay? So the heights on a staircase are quantized. You can only be at certain distances or certain heights. And that's the exact same way as electrons in an atom. Those electrons can only be at quantized distances. Therefore, they have quantized amounts of energy based on what shell they're in, okay? All right. I know this is like a very foreign concept to some people because it's so abstract. We don't see electrons, we don't see atoms, we don't see how these things are. So if any of this is really confusing or difficult for you, please let me know, because we are going to do a whole lot with valence electrons moving forward. So what is a valence? We've talked about electrons. We've talked about what a shell is. What is a valence shell electrons? It's an electron in the outermost shell. All right, so if we're looking at this picture, and I drew the electrons in here, I'm going to circle the valence in black. This one is a valence. It's in the outermost shell. The other 3 electrons on the inner shells there, they're not a valence electron. Only the one in the outermost shell. Okay. So, as scientists studied these things, what they found out, we fill in the blanks at the bottom here, elements that have the same number of valence electrons tend to have similar group properties in chemical reactivities. We've actually already seen this. We watched 2 videos of different alkali metals, and we saw they both reacted violently. I don't know if you want to call that reaction of sodium with water violent. I promise you could look up a reaction of a bigger piece of sodium with water and it would be more violent. But we've seen how alkali metals react quickly, even violently with water. They react in a similar way. If you've done the wet lab, I think everybody should have done the wet lab right now, and you dropped, well, actually, I don't know if those elements are in the same group or not. Never mind. We saw how group 1 elements react the same way with water. All right, and it's very similar. You know, here's some group 7 elements. We said that they all tend to react pretty quickly, and they like to react with group 1 elements. Well, why is that? Well, they all have the same number of valence electrons. It all has to do with their valence electrons, okay? All right, so notice here too, I'm going to point out this word group. We said they have similar group properties. Why is that? Well, elements that are in the same group, they have the same number of valence electrons. I'm going to make a note of that. Elements in the same group, that is a vertical column, have the same number of valence, I'm going to abbreviate, electrons. Okay, so remember that. Because in just a second, I'm going to teach you how to count valence electrons. So let's do that. Well, if elements in the same group, and here we're talking about the main groups, have the same number of valence, if you can count main groups, then you can count valence. So remember, any number that has the letter A next to it is a main group. So main group 1 has 1 valence electron. So all the elements here, hydrogen, lithium, potassium, sodium, have 1 valence electron. Anything in main group 2 has, guess what, 2 valence electrons. Now transition metals are different. We skip those, they're not a main group. You can know this, all transition metals have 2 valence electrons. All of them, no matter if they're in group 3B or group 8B, okay? All the transition metals have 2 valence. So we skip them when we're counting main groups. Let's go over to main group 3. Main group 3 has, guess what, 3 valence electrons. Main group 4, 4 valence electrons. You get the trend here. Main group 6, 6 valence electrons. Main group 7, 7 valence electrons. And then main group 8 has a full set, the most, 8 valence electrons. So I want you to know how to count main groups, and if you know how to count main groups, you know how to count valence electrons. All right. So why are valence electrons important? Why do they help determine the chemical properties of elements? Why are these similar among different groups? Well, we discovered valence electrons are the outermost electrons in an atom. We said they're in the outermost shell. Therefore, they are the most loosely held by the atom. What do I mean by that? Let's draw a picture really quick. Let's think about this. We know, remember, that the nucleus is where the protons are, right? So actually, instead of drawing a dot, I'm going to draw a plus sign. Because you know protons carry positive charge. Don't forget that. So that's where the protons are. There could be 1 proton, there could be 20 protons in the nucleus, depending on which element you're talking about. But we know the proton or the nucleus is positively charged. So if we have 1 energy shell around the nucleus, and we have an electron on that energy shell. That electron is pretty close to the nucleus. And remember, electrons carry negative charge, and we know opposites attract. So that electron feels the pull and the attraction to that nucleus quite a bit. More so than if we had an electron, say we have 4 energy levels or layers or shells. Say we have an electron out here. It's further away. There's probably lots of electrons in between this outermost, this valence electron in the nucleus now. So this one does not feel the attraction of the protons in the nucleus as much. So this one is more loosely held. All right. So it can be pulled from the atom more easily than an inner shell electron could. Okay. All because of the pull from the protons in the nucleus. Another thing about valence electrons and about atoms in general, all atoms want to have a full outer shell of 8 valence electrons. A full outer shell of 8 valence electrons. So there's something special about the number 8, that when you have a full outer shell, this equals stable. Okay, we talked about the noble gases earlier and how they're stable. Why? Well, guess what? They have a full outer shell of 8 valence electrons. I will tell you, there are 2 exceptions to this rule. I'm going to box these in green. Hydrogen and helium. Okay, these are exceptions. Okay, hydrogen and helium. Why are they exceptions? Well, I don't think I've explained this yet, but based on what row the element sits on in the periodic table, that corresponds to how many shells are around the nucleus. So what did I just say? Let me erase this over here. This is row number 1, correct? This is row number 2, 3, 4, 5, 6, and we have 7 rows. Okay, so if you're an element on row 1, you're either hydrogen or helium. Here's what you look like. Here's your nucleus. You have 1 shell around your nucleus. Okay, so that could be hydrogen or helium. This first shell can only hold, I'm going to zoom in. It can only hold, I'm going to change colors here, up to 2 electrons. We don't know why, but there's something special there. Once you have 2 electrons in the first shell, you're done. You can't fit any more. So think, hydrogen and helium, they can't ever have 8 electrons in their outermost shell. They can only have 2. So there are exceptions. I'll say they're full. Whoops. With 2 valence electrons. Once they hit 2, they're full. On row 2, so if you're lithium or beryllium or carbon or nitrogen, here's what you look like. Let's zoom in. Here's your nucleus. There's energy shell 1. There's energy shell 2. Remember, if you're on row 2, you have 2 energy shells around your nucleus. Row 2 can have up to 8 valence and any subsequent row after that. All right. So let's say that I am in row 2 and I have 2 valence electrons. Which element am I? Who did I just draw? I have 2 energy shells, so that means I'm on row 2, and I have 2 valence electrons. I just drew beryllium. Okay. Here, this element as we drew it is helium because I have 1 energy shell, okay, but I have 2 valence. So helium as well is kind of an exception in multiple ways because it can only have up to 2 valence. Remember that outer shell on row 1 can only have 2. So I want you to get comfortable with the idea of how to draw atoms like this. And how do if I want to draw a picture of sulfur, let's draw a picture of sulfur with the circles and the electrons. Go back to pink for a second. We see that sulfur is on row 3. And so that means sulfur is going to have 3 energy shells around its nucleus. 1, 2, 3. Now, what group is sulfur in? Sulfur is in main group 6. So it's going to have 6 valence electrons. So I'm going to draw 6 electrons on this outer shell. There's 1, there's 2, there's 3, 4, 5, and 6. Now I'm sulfur. Okay. So I want you to be comfortable with a picture of an atom like this. All right. I'm not saying you're going to have to identify every element with pictures like this, but I want you to be comfortable with that idea and what a valence electron is, what an inner shell electron is, and how to count valence. Questions so far on what we're talking about?
So the row tells you the levels and the group tells you the number of outer electrons.
Correct. The row tells you how many shells or circles we can draw around the nucleus, and the group tells you how many valence electrons, how many electrons are on that outermost shell.
Okay.
Yep, to summarize, that's a good way to summarize it. Okay, lastly, we're going to get more into this with chapter 3, but you need to know that atoms, because there's something stable about having a full outer shell, everybody secretly wants to be like a noble gas. Okay, all the other elements want to be like a noble gas. And so they will give away or receive valence electrons. These are the only electrons that an atom can trade. Okay, give away or receive so as to have 8. Now let's talk through an example, all right? An atom with 5 valence. Let's pick one. Here is main group 5. Okay, so let's just pick the first one, nitrogen. Nitrogen has 5 valence electrons. If it wants to have 8, it can either give away 5, and then underneath it will have a full set of 8, or it can gain 3. And it's gonna go the shortest route. It will gain or receive 3 to achieve an outer shell of 8. Okay. An atom with 2 valence electrons, the quickest thing to do is to give those away to achieve 8 in the shell underneath. So for example, if we have magnesium here, that's group 2. I want to draw a picture of magnesium, and I need some space. Magnesium is on row 3. So here's the nucleus, and here's 1, 2, 3. If magnesium has 2 valence electrons on its outermost shell, there's the 2 valence. On the shell underneath, so that energy shell, we haven't drawn these, but it's going to have a full set of 8. Okay, 8 valence electrons there on the second shell. So it can give these 2. It can give these 2 away, and then underneath it has a full set of 8. And that's quicker, that's better than gaining 6, okay? And we'll get more into this. If you don't fully understand some of this stuff, we will talk about it more in chapter 3 as well. I just wanted to introduce it here. Then lastly, what does this last part say? Elements within the same group, we talked about this, they have the same number of valence electrons, and therefore they trade electrons in a similar fashion, okay? This is why we say elements in the same group behave the same way, because they're trading electrons the same way. And electrons determine everything about an element's chemical properties. If it's highly reactive, if it's inert, or just a little bit reactive, it all depends on how they trade electrons. Do you guys like how I have like every word underlined on every slide when we're done? I feel like I wouldn't do that if we were face to face, but I want you to know what words I'm talking about, and that's the only way for me to point that out on the screen. All right, last concept of the day is what we call an electron dot structure. By the way, any questions so far? If what I'm saying is flying over your head today, or it's hard for you to just understand, that's natural, again, because these are not tangible concepts, okay? This is stuff that's invisible, okay? And we don't think about how electrons move every day, or their energy, or their location. So I promise this is gonna make more sense big picture when we get to like chapter 3 and 4, but we have to understand some of this foundational stuff to get to that. I would suggest, again, you should be reading the textbook along with this, and the textbook probably says it in a different way than I do, and that may help you to hear it in a different way. Let's talk about electron dot symbols. This is just, or structures, symbol, structure, same thing. This is just a way to express the symbol of an element and to see how many valence electrons it has. We use dots, okay? So if you're in group 1A, All you do is you write the symbol and you put one dot to indicate one valence electron. The only the only rule you have to abide by is that every side of the symbol should get one dot before any side gets two dots. Okay, so notice group 4, we don't draw carbon like this. Okay, and we don't draw carbon like this. We don't do that. We put one dot on each side, and then when we get to group 5, well, we've run out of sides, so now we can double up and put 2 electrons on one side. Okay. Again, helium is an exception. Yes, it's in main group 8, but remember, it's on row 1, so it only has one shell around its nucleus, and that first shell can only hold 2 valence electrons. So that's why the structure for helium, the electron dot structure, only has 2 dots. And I would argue with how they drew it. I don't like the way they drew it. I would draw helium like this. 1 dot on each side. Everyone, they're breaking their own rules. All right. Questions on electron dot structures. We're going to do a practice real quick. So we have 6 elements here. I don't want you to look at the slide above. Don't want you to cheat. I want you to draw or figure out the number of valence electrons and then draw the electron dot symbol or structure for each of these elements. So if you need to get a periodic table, use that. There are plenty of pictures of periodic tables from these lecture slides. Let's talk about krypton. Where is krypton? What main group is krypton in? Anybody know?
8.
Yes, main group 8. So that means it has 8 valence electrons. Because remember, the number of valence electrons matches which main group it's in. So if we're going to draw the dot structure, put 1 dot on every side. There's 4. Now I have to double up. 5, 6, 7, 8. Okay, carbon. What main group is carbon in?
Four.
Thank you, Aubrey. 4. So it's got 4 valence. And remember, carbon, we're going to put 1 on each side, and we're done. Calcium is in main group
2.
2. Okay, so it's got 2 valence. And you should put 1. It doesn't matter if you do top or bottom, left or right, just as long as you put the dots on 2 different sides. Potassium, you guys should know immediately its main group. 1. Oops, why did I draw a K? I don't know. 1 valence, because it's in main group 1. Thank you, Brendan. So we're just going to do K with a dot. Boron, B.
Group 3.
3 valence. And we'll do dot, dot, dot. Chlorine is a halogen, so that's main group.
7.
7. So 7 valence. So I'm going to put 1 dot on each side. There's 4, 5, 6, 7. Okay. Wow, we're early again. I'm sure y'all don't mind. So I'm done. That's what I wanted to get through today. That's the end of chapter 2. Make sure you are paying attention to that chapter 2 homework. I'm going to stick around and work on a couple problems for the dry lab if anybody wants to see that. If not, see you later. Have a great Labor Day weekend, and I will see you on Tuesday.
So I sent you an email this morning, and I know you answered, but the thing that I clicked on, the thing I thought was a test, it's like locked out and I can't get back in. Can you reset it for me, please?
Yeah, was it for the wet lab? That
Yeah.
should be enough timed. Yes, I will. I thought I cleared your attempt. Is it not letting you back in?
It hasn't. I don't know if I didn't click on it right or what.
Let me make a note of that, Janelle, and then I will, when I get off of here, I'll do that for you, okay? So try again in like 30 minutes.
Okay.
Thanks for reminding me. Reopen. Okay, any other questions before we look at some dry lab stuff? Okay, well, Hannah, what dry lab questions did you have?
The ones about specific heat, number 3 and 4, I'm having trouble with like switching what we're trying to find.
Okay, number 3 and 4. Let me pull it up on my iPad. Give me just 1 second. I'm gonna upload this file to my Google Drive. Let's go here. So I'm having to grab it off my computer real quick. Okay. And oh. All right. So I'm gonna, oh, did I already have it? I already had it. All right, here it is. Let me share my screen again. Okay, here's the dry lab. You said specific heat. Number 3, right? Okay. Looks a little small. Can y'all see that better? Okay. A quantity of water is heated from 25 degrees Celsius to 36.4 by absorbing 325 joules of heat energy. What is the mass of the water? So how much water do we have? So first off, can someone tell me, we have several of y'all still here, can someone tell me what equation we need to be using for this? And if you don't know, it's in our lecture slides, the slides where we talked about energy and specific heat. What is that equation?
The specific heat one?
Yes.
Oh, specific heat equals calories divided by grams times degrees Celsius.
Now remember, it can be calories or it can be joules. Okay.
Where did you say that we can find that equation?
It is in the lecture slides. So measurements. Do y'all remember measurements?
Yeah.
It's in this lecture, and close your eyes for a second. I gotta scroll up. Before we talked about density, we talked about energy. Y'all remember this slide?
Yes.
All right, here's our equation right here.
Okay, yeah, that's right.
Okay, so here we have an energy term with units of joules. So I'm actually not gonna work this in calories. I wanna work it in joules because the energy term that I'm given is units of joules, all right? Now, it's important to know too what substance you're talking about. We're talking about water. So we need to solve for the mass of water. So which term in this equation relates to mass?
Grams.
Grams. So Hannah, how do we need to get grams by itself?
This is what I'm having trouble with. I'm
Okay.
not good at this.
Okay. So to get grams by itself, we're going to do some algebra. We're going to cross multiply. All right, so what I'm going to do is I'm going to multiply. I want to get grams by itself, so I'm going to multiply both sides of the equation by grams. If I do it to one side, I have to do it to the other. Then, like always, when you have something on top and on bottom, it cancels. Now, if something cancels, It goes away, right? So now here is what we have. If we paused our equation, we have grams times specific heat equals joules divided by your change in temperature. We're almost there. What do we need to do next to get grams by itself?
Divide by specific heat.
Yep. Cancels. Sorry, everyone. My husband's calling. Decline. I don't know how to, oh, I can hit on that. Okay. So now specific heat goes away. So now we are left with G. Man, I sure am glad. Some people I know you have like really fun names for like your close friends or your spouse. I'm so glad I don't have like an embarrassing name for him on my phone. That could have been great. J divided by specific heat times degrees Celsius, okay? It doesn't matter what order you write these things in as long as they're both in the denominator, right? Okay, so here's our equation. And what I like to do is put these in parentheses. Because if you don't, I guarantee you, some of you in your calculator, you're going to put in the number for joules, and then you're going to divide it by the number for specific heat, and then you'll say times degrees, times your change in temperature. And your calculator will read this as a multiplication when actually it's still you're dividing by your change in temperature term. So that is why I say put these parentheses in your calculator around these numbers, okay? When you go to divide, so that you mathematically get the right number. All right, so Hannah, that's the equation you need.
Yes.
I think you should be able to do it from there. To solve for grams, you need to have the joules, which the problem gives you. You need to have your, remember this is delta T, your change in temperature. Can you find the change in temperature from the problem?
Yes.
Okay. Now, what are we going to plug in right here? I don't see any other numbers.
It's on the graph that you gave us on the slides.
Who said that?
Me?
Who's me? I can't see. Oh, Hannah? Oh, hi, Hannah. Yeah, we're talking about water here, so you're either going to pick 1 or 4.18. Which one do you need?
Joules, 4.18.
Yep, you need the one that's got joules in it, so 4.18. There you go. Sorry, let me respond to this text. The ones. Okay. So I think that should get you through problem number 3. Any other questions? You said there was one more.
I said number 3 and 4, but I think I got it now.
Number 3 and 4?
I was just confused about how to get it by itself.
Yeah. So number 4, you are, it says, what is the change in the compressed temperature? So you're going to start out with the same equation. So I'll just do this real quick in case anybody else has a question. Now notice your energy is still given to you in units of joules. So I'm going to work with joules here. And your specific heat is in joules, so that's good. If you were ever given an energy term like this in joules, but your specific heat was calories per gram degree Celsius, you're going to have to convert something. You're either going to have to convert your energy to calories so that it matches, or you would have to take your specific heat and convert that to joules so that it matches, okay? The energy term and the specific heat term, they have to match. They have to either both be calories or both be joules. All right, so we have joules and then gram degrees Celsius. So you're trying to find the change in temperature here. So you'll just multiply both sides by change in temperature. Cancel, cancel. divide both sides by specific heat, cancels, and then you're left with degrees Celsius equals joules per gram times specific heat. And again, always put that in parentheses. That's the equation you use there. Okay. Sometimes the hardest part, well, not sometimes, always, the hardest part is just lining up your equation, getting the equation the way you need it. Then you just plug numbers in, right? Okay. Good deal. Any other questions?
Can you go through number 2?
What?
Okay, there were 2 questions there. Someone said, can you go over number 2?
Yes.
Okay, and then what was the other question?
I was gonna ask a question about the due dates, but we can do number 2.
Okay, due date for this dry lab?
Just your due dates and because I remember you said that everything is due like a day before.
Oh, that's
And-
the homeworks. That's the homeworks.
Oh, okay. So I
Yeah,
was
if
trying
you,
because I thought that
Janelle, if you'll go to the syllabus and you'll read the portion that says homework, I think you'll understand that perfectly.
okay.
Yeah, and let me know if you have questions about it after that. It's just the homework that's due at midnight the night before on the day that it's stated on the syllabus. Dry labs are due if you'll look at the Blackboard assignment due dates. Yeah. Okay, number 2, this one right here.
Yes.
Okay, I actually made a video step by step on how to solve this. It's posted on Blackboard.
Okay, then we're good then.
Yeah, but I will tell you, attempt it on your own first. I think it's the most challenging one, which is why I picked it to do the video.
Okay.
Because you have density here. Why are you given density? And then this right here is not a mass, it's a volume because it's a cubic distance. So try it. If you get frustrated with it, check out the video and go from there. Let me know if you have any questions.
Thank you.
You're welcome.
Actually, I have a question on the number 3 one, because when I typed in the like equation and like plugged in the numbers, there's not technically an exact right answer when you're looking at the dry lab.
Like you're looking at the multiple choice question on Blackboard?
Yes.
Hannah, do you mind telling me what you get?
I got 6.820 and a bunch of other numbers.
Is it close to any of the answers on Blackboard?
Yes.
Okay.
There's
Well-
one that's 6.813.
Okay. So you got 6.8 and then there's an answer that's 6.81.
Yeah. Well, I got
Oh.
6.820.
Okay. Then you're close enough.
Okay.
Yeah. I would go with the one that's, you're like not even a tenth of a decimal off.
I just
Yeah.
want to make sure.
You bet. Okay. Any other questions? Y'all get out of here. Go have fun. Bye, Olivia.